All right, let's get going. Good morning, everybody. Welcome to another exciting morning of Chem 1211 with your host, me, Dr. White. Howdy. And I found out this morning, which happens about once or twice a semester, I forgot we went through the equilibrium practice problems last week, which is a good thing since I looked at the video, I can do that. And I saw I've done it, but still, let's go back and do a couple, and then we'll do a couple pH problems, and then we'll do the lab, and you'll get out before midnight. Uh, all right, if you notice, and thumbs up people, do you see energy diagram? Thank you. Here's the energy diagram. And remember, an energy diagram, you have energy on the y-axis, time on the x-axis, and then you start with a certain amount, which you arbitrarily, the energy of the reactants, remember left reactants, right products, and you look at, is this exothermic? If heat is on the right, it is. If it's on the left, it's endothermic. And when you have an exothermic reaction, the energy of the products minus the heat is always lower than the energy of what you start with. For a endothermic reaction, it's the opposite. The products have more energy than the reactants. And in both cases, from where you start to the top of the hill is the activation energy. And the activation energy is the minimum amount of energy you need to get over that hill. And getting over that hill means you have a chemical reaction. I'm going to rate it not as an equilibrium for this one, but we'll come back to this. And the question would be, draw the energy diagram for this reaction, and be sure to indicate the activation energy on there. Your turn. Today isn't cut class Thursday, is it? I could understand if I had an 8 p.m. class, some people would be late, but 9 a.m.? I've been up working since about 6 a.m. And thank you for coming. And for those of you who got here on time, what I said earlier, wink, winks, hint, hint, say no more, was true. I'm looking at all of your work. Remember, today is Thursday. Turn on your webcam. So all you people who I have never met before or seen your face, please turn on your webcam. You don't want me naming names, do you? Actually, I can do that by, if you see your name on the screen now, turn on your webcam, please. Pretty please. Double pretty please. All right, I think everybody's done. Thumbs up, people. Are you done? They are. So how do we do this? Energy diagram. You don't have to put X and Y on there, but I will. On the Y-axis, we have energy. And it goes up that way. On the X-axis, we have time. Sometimes I've seen that written as reaction coordinates. I like time because reaction coordinates confuse students. Now, if we look here, remember the total energy on both sides is the same, because in our universe, our world, you never create or destroy energy. Therefore, the total energy on this side is equal to total energy on this side. And arbitrarily, I will do this, carbon plus water. Now, if you notice, carbon plus water has a certain amount of energy, and then the total energy on the left is including the heat. And if this equals the energy on this side, then carbon monoxide, CO, and hydrogen have more energy. And how high, don't worry about it. And then you go up the hill and down the hill to grandmother's house we go, actually to the product. And I gotta change my angle of my pad because it looks like I'm writing at an angle. I am. And from where you start here to where you end up, the top of the hill, that's the activation energy. Now, can everybody see at the bottom of the screen, 2FeBr equilibrium? Write the equilibrium constant for that. And this is one of those things I won't give an important information, but remember the equilibrium constant is equal to the concentration of the products, gesundheit, whoever just sneezed, concentration. Dr. White has good eyes. Ears, no. Eyes, yes. The eyes have, oh, it's awful humor day. But anyways, the equilibrium constant is equal to the concentration of each product on the top to the power of the coefficient divided by the concentration of each reactant to the power of that coefficient. And why don't you give it a try? This will not be an important information. I'm going to be mean and make you memorize a few things. And Liliana, the answer is yes. In an equilibrium, when we're talking about the equilibrium constant, what we call the product is always on the right. As always, thank you for your question. All right, let's try a poll. I haven't done that yet today. Hold on. This is the wrong poll. Ah, I should go back to breakout rooms. This is the right one. See, I wasn't lying the first day. Even I make mistakes. All right, looks like all the voting public is done. So let's do this. All right, if I come over here, oh, look, it's already done. And notice the coefficient for ferric bromide, FeBr2, is 2. So it's this concentration to this power times, remember, common mistake, students, instead of put that, they use a plus sign. And I've always wondered, will they see that and think this is wrong, don't do it. Times the concentration of bromine, and notice the coefficient is 1, divided by the concentration of ferrous bromide to the power 2, because the coefficient is there. And if we look at the next one, you can see the same thing. HBr on the top to the second power, concentration of hydrogen, and concentration of bromine. And that's how you do equilibrium constant. Now, I should tell you, one of the things I don't do, some instructors have problems with this chapter where they give you the actual concentration in, not concentration, but how many grams per volume. Then each one you have to calculate the molarity, and then you have to put it in this equation that you have to generate and calculate the EQ, equilibrium constant, KEQ. I've never done that, never will, because I've never done that as my profession. You always have the concentrations available to you. All right, next, let's talk about the relative amounts of reactants and products. And for this one, predict the relative amount of reactants and products for the following. And let's do B. Let's see if I can just sneak it in so you can't see the answer yet. Let's do, can you see C at the bottom? And in case you're having troubles, I'll use my instant font enlarger. And the question is, predict the relative amounts of products and reactants for the following. And let's do 2NO goes to nitrogen and oxygen. And the equilibrium constant is 1.0 times 10 to the 30th. I'm going to work you hard today. Where's my bullwhip? Oh, I need to buy a new bullwhip. And yes, I do know how to buy a bullwhip. I taught myself how to crack one by the time I was about, 14 or 15. I wanted one, and I finally went out and bought one. And that was my all-time favorite. It was a 16-foot all-leather bullwhip. And when my timing was good, when I cracked it, it was louder than an M80 firecracker. Don't tell anybody, Dr. Whiteson's unusual weapons. And yes, I have 2 boomerangs and a number of sets of nunchucks. No samurai sword. I always wanted one, but I have never bought one. Samurai Dr. White. Or ninja. I'll come one day in all black. That's the one country or area of the world I never got to, Asia. I was supposed to, but the trip was canceled and the people I was supposed to train, they sent to me instead of me going to Tokyo. Oh, was I upset over that. All right, everybody done? Well, you are not. Well, I shouldn't say that. And the question is, someone has a question. And Gabrielle, the answer is yes, unless I decide to say it again, instant replay. If you go look at the two videos, I try and do the same thing in both. I don't know about the jokes, but you're right. So do you feel, how should I say this, honored to have jokes nobody else does? Well, it's on the internet. All right, let me get back to work. I'm getting sidetracked. All right, how do you determine this? Let's go up here. If K equilibrium is greater than 1, concentration, let me give myself some room here. The concentration of products is greater than the reactants. If K equilibrium is much less than 1, it's the opposite. And if we look here, it's a positive number and big, therefore it's much greater than 1, and therefore that's what those 3 dots mean. The products are greater than the reactants. Now let's do one more in this area. All right. Thumbs up, people. You see number 11 on there? What happens to the concentration of carbon monoxide, CO, and hydrogen gas, H2? And I'll write it up here. If you put the reaction in an ice bath. And this is your turn Thursday.
Oh, for me, it doesn't really too much matter, but I prefer to be called Gabby.
Thank you. That's why I asked. I remembered. I'm looking at your name on your under your screen, but it dawned on me. So guess what? Hi, Gabby.
Hi. How you doing?
I'm doing pretty good. Hopefully you're
Good.
doing good too. Bet you never thought you'd be smiling in a chemistry class. All right, anybody need more time? Or I should say, thumbs up, people. If you're done, give me a thumbs up. Those of you without your screen on, use the symboli. Remember, Dr. White changed it. I'm not using emoji, I'm using symboli, which is Zoom talk for this, the thumbs up symbol. I guess you could do it on Twitter too. All right, let's do this. And the question is, if you put the reaction in an ice bath, what happens? Ice bath removes heat. At equilibrium, there was a certain amount of heat. Now there isn't enough. And it goes, oh no, I don't, if you listen hard, it does say that. Oh no, I don't have enough heat. I need more heat. How can it make more heat? If carbon dioxide and hydrogen react to make more heat. But when you make more heat, you also make more carbon monoxide and water. Well, if you make more of something, what happens to the concentration? It increases. And when you react something like the hydrogen, what happens is consumed. Everybody remember my French silk pie? I still haven't bought and I shouldn't, so I won't. I'm still trying to undo the pandemic weight gain, but that's another story I'm not going to get into today. And hydrogen is consumed when you consume something, the amount, i.e., that is the concentration, decreases. And that's how you do it. Any questions on that? All right, since we already did this, and I don't want to cheat you out of a full day work, let's do some pH stuff. Even though Monday I'll go through the pH problem set, but let's do some pH stuff. And through the miracle of I know chemistry, I can do my own problems. That was lame. All right, let's do this. And important information, I would give you this. And it's your turn. Oh, let me make it relevant. Does this help motivate you? Actually, I do that because it does. Keep an eye on me, I'm very sneaky.
Dr. White, can you read the pH again? I can't read it. I'm sorry.
All right, mean the number or the equation?
The equation at the bottom.
All right, let me help you out. Does that help?
Yes, it does. Thank you. I'm sorry.
Whoa, stop, stop, stop. You should never, ever in my class say you're sorry for asking a question. That's a good question. If you can't read it, you should ask, what the heck did you write there? I can't read it. You might be more polite like you did it, but you should never, ever in my class say you're sorry for asking a question. Doesn't mean I'll answer all of them because I still haven't figured out what's the meaning of life. Well, that is a question answer. I haven't figured it out yet. So I will answer all questions. If you ask me for my social security number, I'll say, no, I won't give it to you. And I answered that one too. Now I'm doing things my father told me not to do. Never tell a kid not to put peas up his nose with his knife. And when you're done, give me a thumbs up. Oh, I see a lot of thumbs. Nobody did a thumb puppet on their thumb. I haven't thought about that since first grade. All right, let's do this. What are we being asked to find out? pH. What are we given? The hydronium concentration is this. And what do we know? Well, you're given this. The pH is minus the log of the hydronium ion concentration. I think it's about time to change the tip on my stylus. And when this number is 1.0 times 10 to the minus x, then the pH is x. So in this case, the pH is 3. Now you're also, oh, that's weird. I don't know why that didn't stay on the paper. Now, this is something you have to learn, and I think it's something important for the rest of your life, and that's the pH scale. And pH scale goes from 0 to 14. 7 is neutral pH. Below 7 is acidic. And above 7 is basic. If you notice, 3, and I hope you know your numbers, which are smaller and larger, from 0 to 14, 3 is less than 7. So the answer is this is acidic. Anybody know why your stomach fluids are acidic? Chem 1211 answer, not biology answer. Time's up, and the answer is because there's an acid present in your stomach. I keep on always being amazed. I amaze myself, that's not hard, but anyways, truly, one of the wonders of life is that I have cells and you have cells in your stomach that synthesize, that's the fancy word for makes, hydrochloric acid. That's quite strong because that's how you break down your food. If you take organic chemistry, which I don't teach at COD, I still teach at ECC, Elgin Community College, I would teach you the actual chemical reactions involved. Did you know you're a walking chemical plant? You are. All right, let's do another one. There's a little motivation for you. Can everybody read that? If not, I'll translate it. If the hydroxide ion concentration is equal to 1.0 times 10 to the minus 3, then what is the pH of the solution? And important information I will give you. By the way, you can look at it in the lecture folder of Blackboard. It's already up. pH equal minus the log of the hydronium ion concentration, and Kw, which is named after me. No, I wish it was. Every time I see it, I think, oh, it's after me, is the hydronium ion concentration times the hydroxide equal 1.0 times 10 to the minus 14. Your turn. Have fun. And while you're doing that, a public service announcement from me, the management. Don't forget, next week is the deadline for the extra credit project if you're doing it. And there's no late submissions accepted. Also, I've now lowered the hammer. The lab that's due today, if you don't get it in, I think it's by Saturday, you get 0 points. Also, Saturday is the deadline for past labs, which you can upload to the assignment area of Blackboard. And as I mentioned on Wednesday and sent out in an email, if after Saturday you don't have your past labs handed in, you will get 0 points. And you shouldn't, because they're easy points. My labs aren't that hard. At least I think not. Hint, 2 steps. Double hint, 2 steps. I wonder where everybody is. Must be that snowstorm out there. Oh, by the way, I forgot to mention yesterday, I hope everybody the day before enjoyed summer, now that we're moving into fall again. And while you're doing that, I'm going to look up something on the internet I want to use. Be with you in a minute. I can't find it right now. All right, sorry about the delay. I was looking for something and I couldn't find it. All right. Everybody see the problem on the whiteboard now? All right, let's do this. What are we being asked to find? The pH. What are we given? The hydroxide ion concentration. And we're also given the pH is this and Kw is this. And if you notice, you need hydronium ion concentration due to pH. And oh no, Dr. White didn't give them to you. Oh, is he mean today? So how do you do this? You need 2 steps. And step 1, you solve for the hydronium ion concentration. How do you do that? You use this. The ionization constant, Kw, that's me, no. is hydronium times hydroxide is equal to 1.0 times 10 to the minus 14th at room temperature, which is what I'll always do. And how do you solve for the hydronium? You get rid of the hydroxide. And how do you do that? Well, in a multiplication like this is, I'll divide by hydroxide. Whatever I do to one side, I have to do to the other. And I did. This cancels out. I now have this. I know that this number right here, if we scroll up, 1.0 times 10 to the minus 13th. So I'll put it in. Times 10 to the minus third. I think I might have said something wrong here. Let me clean this up. And this is equal to 1.0 times 10 to the minus 11. Now, are we done? No, because we're trying to find the pH. So now we do step number 2. Determine or solve for the pH. And pH equals minus the log of the hydronium concentration, which we just figured out right there. So I'll put it in minus the log of 1.0 times 10 to the minus 11. And this is equal to 11. And that's our answer. By the way, that's basic. It's above 7. I definitely do think later today I'm going to have to change the tip on my stylus. Let's try something. Or I just have a heavy hand today. And here are 2 more for you to do. What happens to the numerical value of the pH of a beaker of water at pH 7.0 if you add a few drops of H2SO4, B, add a few drops of NH3? Your turn. All right, I think everybody's done. Is everybody done? Let's go and do it. All right. First of all, you should know, and I've talked about this, H2SO4 is an acid. You should also know the pH scale. And below 7 is acidic, above 7 is basic, and I don't have enough room at it, so I can do it on this side. 7 is neutral. Now, when you add more acid, and it becomes acidic. which I'm not asking that. I'm asking what happens to the numerical value. And when it becomes acidic, the numerical value will decrease. Or it goes down, gets lower, whatever. Now, ammonia is a base, very strong base. And if I move my face here, which I just did, if you look at the pH scale, when you add a base, something becomes basic, the pH will increase. And those are things you should know. And you should know, such as HCl is an acid, HNO3 is an acid, H2SO4. You should know KOH, NaOH, and ammonia are bases. Any questions on acids and bases? Right after the break, we'll do the lab, which deals with titrations. And with that, let's take a 5-minute break. I'll be back. I like my Arnold Schwarzenegger impersonation. Pretty awful. But anyways, I'm going to go stretch. I'll see you in 5. I've used this all day, so I better use it now. It's time to start again. Everybody, let's get going. Ring, 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 ring. I gotta buy myself a bell. Everybody back? All right, let's get back to work. Today's lab is an important lab that teaches you a new technique and something that's done in the United States, I would say, thousands of times every day in chemical plants and other plants that use chemicals, and that is titrations. And today's lab deals with acid-base titrations. Everybody see acid base or titration of an unknown? Okay, thank you. All right, so today's lab, titration is when you add a known amount of an acid or base of a known molarity to a known amount of an acid or base of an unknown molarity. So if you start with an acid you don't know, you're going to titrate it with a base you do know the molarity. And if you look at the lab, I tried to help you out. First of all, equation one, when at neutralization, that's when the pH indicator changes color, the following is true. Moles of acid equals moles of base. Now, you can boil this down to milliliters of acid. Doesn't sound right. You can obtain from deriving from here to equation two, the equation that milliliters of acid times the molarity of acid equals the milliliters of base times the molarity. And this is true for a monoprotic acid. That means it only has one proton, H plus, it can give up, which is what we'll do in this course. Sulfuric acid is diprotic, we won't do in this course. Now, in this lab, you'll be determining the molarity of an unknown HCl solution, HCl, hydrochloric acid. Now, just to show you how how to get to that molarity, if you have milliliters of HCl times molarity of HCl, milliliters of acid times molarity of acid equals milliliters of base NaOH times molarity of base NaOH. How do you solve for molarity of HCl? You divide both sides by the milliliters of the acid. And therefore you come to equation 3. And in this lab, you'll be doing a titration and determining how many milliliters of sodium hydroxide of a known molarity will neutralize a known amount of HCl. And that's what you'll be doing. Now, let's go to Beyond Lab Z. So, thumbs up, people. Do you see welcome to vid? All right. Now, watch closely. Let me move this out of the way. Where it says worksheets on the left, if you scroll down, let me scroll down, you'll see acid-base chemistry. Click on that. Oh, look, a whole bunch of choices. And scroll down until you see acid-base titration of an unknown HCl solution. I'm going to click on that. And does everybody see the lab right now? Can you see that right now? Okay. Now, right here in the center, this glass tube with this orange stick, which is called the stopcock. It's a valve. I don't know how it got the name stopcock, but that's what everybody in chemistry calls that kind of valve. I'll have to look that up on the internet this weekend. And inside, they've already put water and your unknown. If you notice over here, you can see unknown 12. You'll need to record that. And here you have a known sodium hydroxide solution. What do I mean by known? If you look on there, it says 0.2564 capital M. Oh, you know what capital M is? That's molarity. So we know the molarity. Now, over here in the upper left-hand corner, they have the burette. They've already filled it with sodium hydroxide. And notice that it has a meniscus. Meniscus is when you put a liquid in a tube like water, it doesn't go straight across, it forms like a U. Everybody see that? And you measure the volume at the bottom of the meniscus, and they were nice enough to put it at 0.00. Now, if you look at the meniscus, at the burette, notice as you go down, the number increases from 0 to 1. That's telling you how many milliliters you've added. Now, each line in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the big one, 10, is 1/10 of a milliliter. And you can also see in between that, and you can get 3 significant figures. So I can say this is at 0.00. Is everybody clear on that? And if the line were right here, it'd be 0.10, because each markings is 1/10 of a milliliter. Now, since I've done, I hate to say this, if I had $1 for every titration I did, I could go to Europe and have a nice vacation. And then probably elsewhere. I've done a lot of these in my life. In fact, one laboratory I managed, QC quality control lab, every morning, one of my chemists, or two of them, used to do about 75 titrations. And I thought, God, that's got to be boring. I found a way to automate it with an auto titrator that freed them up to do more challenging stuff. Now, let me teach you a trick on how to use a burette. Now, first of all, this is the trick part. If you slide it up, notice it's going very slowly, and you can adjust or stop it. When it's the bar is horizontal this way, it stops. When you turn it all the way like this, see how fast it's going? And you can control it to go slower, slower, dropwise. Now it's off. Now, here's the trick. You don't know what the amount you're going to have to put in here is. And there's a term, and I don't know how it got started, but we use it, at least I've used it in every lab. We're going to do one waste titration where we'll shotgun it in to see where our endpoint is. Now, in titration, the endpoint is when this liquid has a pH indicator. Now, for this lab, they use bromocresol green, which goes from a yellow to blue. I just found out this morning, and I haven't mastered it, unfortunately, for you people. I won't change it tomorrow for the other lab that normally use phenolphthalein. Phenolphthalein goes from clear to a wine-colored purple or red, however your wine is, and it's the main pH indicator used in a lab. But they set this lab up, and I only found this morning when I asked, hey, why don't we use phenolphthalein? I got a procedure which I haven't mastered how to change it. But watch closely. I'm going to shotgun it in. Oh, do you hear the sound? Keep your eye on the beaker. Stop. And if you look, it was about 19, actually it was more like 17. If we come over here, if you notice, the blue line is the pH. I like using an indicator instead of a pH meter unless you're automating it. And as soon as it goes up, that's your endpoint. If we come down here, it was about 16 or 17. So the first thing you should do for this lab is practice with turning this on and like that. And it's fun. In real life, it's fun too. You can tell I'm a chemist now. Now, exit the lab. Oops, that's not what I wanted to do. Sorry about that. I pushed the wrong exit. Now we're back to, everybody see the lab on their screen again? And it's back to 0. And now what you'll do is measure, put down the initial amount, then slowly add this till you see a color change. And that's your final burette reading. And if I do this right, you would go like this. Let me show you a technique. First of all, since you know it's about 16, I can shotgun it in and it saves a lot of time. So I get close to that, and now I can just add a little at a time. Sounds like a metronome. Oh, that reminds me, my sisters used to take piano lessons. Now I'm getting close to where I think is the end point. I'm going to slow it down. See how I stopped at this? Now you're watching a master at work. Modest, aren't I? But anyways, that's how you do it. You shotgun it, do the first time. And now I'm going to ask you to do 2 of these runs. You'll exit like this, and you'll go back and click on unknown HCl. You'll do the titration again. Whenever you do a titration manually like this, you always do it in duplicate to make sure you're getting similar results. Now, everybody see the lab on their screen now? Thank you. Now, if we scroll down, the procedure I just talked about is right here, and you can read it at your leisure. Now, being a nice person I have table 1, and you're going to do 2 runs, titration 1 and 2. Now, if you look at, which is available to you, you don't have to. Everybody see acid-base titration 6.-9. You don't have to read this. I did for you, but in case you can't read the screen, here's the molarity of the sodium hydroxide. Now, important thing, which I put in the table already for you, how much HCl solution are you using? And they tell you 25.00. And what you'll do is put in the molarity. I just gave you that number, it's on the bottle. Your initial volume, like ours was 0.00, your final volume, let's just make up a number, 16.55, and then the total amount used. I think you can figure out that's final minus initial, and then the molarity. How do you do the molarity? You come up to equation 3, put in your milliliters of NaOH, your molarity of the sodium hydroxide, which is on the bottle, and the milliliters of HCl, which is 25.00. And that will give you the molarity of HCl. And if you notice, oh no, he did it again, there are questions for you to do. And I have these questions here, and there's some good ones. I always try and do good questions. And that's today's lab. Any questions about today's lab? And with that, I'm done for today. If anybody has any questions about anything, I'll stick around for a couple of minutes, or more than a couple of minutes if you need me. And with that, I'll say, I'll see you on Monday. And don't forget, on Monday, we'll do the acid-base problem set. I'll also do my world famous review for test number 4. And if you have questions Monday night on anything, including if you're doing the extra credit project, I'll be there. And with that, I get to say, gang gesund, goodbye. And if it rains, so I can't mow my lawn today, I'll probably do it tomorrow. With that, gang gesund. Bye, everybody.
Have a good day, Professor.